Hey everyone, this is Paras Chopra, and today I'm with Professor Donald Hoffman, who is Professor Emeritus at the Department of Cognitive Sciences in University of California, Irvine. He studies evolution and how that impacts consciousness, reality, perception. It's a beautiful mix of two of the most amazing ideas humanity has encountered: evolution and obviously consciousness. We all know how fascinating that is. His TED talk on perception of reality has been watched over 3 million times, and his recent book, The Case Against Reality, I have it with me. It's a beautiful book, and in it he lays out how our reality is an illusion crafted by evolution for helping us reproduce and survive. And that is what we're going to talk about today. But before that, I must welcome Professor Donald Hoffman for taking time out today.
Thank you for having me, Paras. Great pleasure.
Fantastic. So before we dive into this bold conjecture of yours, which is that physical reality per se may not exist, but it's an interface that evolution has crafted to help us survive and reproduce, and all the implication that produces for our understanding of the world. I'd love to understand more about your career trajectory. How did you end up asking this question and getting interested in this intersection of evolution and consciousness?
I first got interested in perception when I was an undergraduate at UCLA. And I took a class on visual perception and found the neuroscience of visual perception really fascinating. It was amazing what these neurons were doing. And then I took a class on artificial intelligence, and that had some papers that we studied by David Marr, who was a professor at MIT at the time. And his idea was not just to know the neuroscience, he had his PhD in neuroscience, but you needed to understand what problems the perceptual systems were solving. And so he said we needed to actually build artificial intelligence, robotic vision kind of systems. And if we could build systems that worked, then we would have some confidence that our theories might be okay. And so I love that idea. So I had the good fortune of going to MIT and being his student. He unfortunately died very young while I was still his graduate student. So he wasn't there for my whole time, but his impact was lasting on me and the entire field. The idea of being mathematically rigorous in our understanding of perception. So that was, Marr really got me thinking about, we could do this with mathematical rigor. And then I began to think that we could get a general theory of perception. We were studying specific kinds of perceptions, but I realized that the mathematics might allow us to start getting a general framework for understanding perception more generally and rigorously. And so I worked on that with some colleagues, Chetan Prakash and Bruce Bennett. And then I began to realize that the mathematics was telling me something surprising. Like everybody else, I was a physicalist. I just assumed that our perceptual systems recover the true structure of the world, right? That's what they do.
That's the default thing we're baked in.
And that's the way my advisor, David Marr, thought about it. He said our sensory systems evolved to tell us those aspects of reality that we need, like the shapes of surfaces and so forth. We recover. We get a projection onto our eyes or onto our sensors, if you're a computer, onto the sensors of a three-dimensional world. You get a two-dimensional projection. So you have to do inverse optics. You have to recover the true three-dimensional shape of the real world out there. So I bought that. That seemed pretty reasonable. And so I worked in that framework for quite a few years. But then I began to look at the mathematics, and it seemed to be telling me that we were creating what we're seeing. And that began to open up possibilities. If we're creating what we're seeing, how do I know for sure that what we're seeing is the truth? And it began to occur to me that maybe this is more like a user interface. And so I wrote a book called Visual Intelligence and published in the late 90s, where I talked mostly about just practical aspects of vision, how vision works. And at the end, I talked about it as a user interface. But I hadn't really done any work on evolution to sort of support that. It was just more an intuition. And so no one really picked up on it. And I realized that no one was going to pick up on it unless I took it further. I needed to actually learn evolution. So I had to learn evolutionary game theory, because that's what the mathematics of natural selection is. So I got a couple of really good graduate students, Justin Marr and Brian Marion, to work with me. And we all learned evolutionary game theory together. And for their dissertations, they started writing simulations. And they did some really fantastic simulations that showed that organisms, simulated organisms that saw reality as it is in our simulations, could never outcompete organisms of equal complexity that we didn't allow to see any of reality, and they were just tuned to the payoffs, the evolutionary payoffs. And we learned why. I mean, when I went into it thinking that maybe the reason why we wouldn't see reality as it is that it would be too time-consuming and too expensive. It's just computing the truth would take too much time and energy. And that's true. It's unnecessary. It takes time and energy. But what we really found, and this was an insight again from my students, simulations, and Brian Marion and Justin Marr, the insight there was that the fitness payoffs in general will not actually have information about the structure of the world. They will erase. So it's like playing a video game, right? If the fitness payoffs in evolution are like the points that you get in a video game. And as long as you do the right actions in a video game and get the points, you can survive to get to the next level of the game. But there's nothing in those points that tells you about the reality, the supercomputer, right? The diodes and resistors. And there's nothing, you can't figure out from what gives you points to how the computer works at all. And that was the deep insight, is that fitness payoffs are about keeping you alive. And what keeps you alive generically is not going to be the same thing as knowing the truth. And so then I went to a real mathematician, Chetan Prakash, a brilliant Indian, now a US citizen mathematician. And he and I had worked together for decades. And so I brought him this idea and the sketch of how we might go after it, but I'm not a mathematician and he is. And he brought home a couple really good theorems. Basically, what we published was two kinds of proofs. One, that it is the case that fitness payoffs erase information about the structure of the world. And what that means practically is, since evolution can only tune our sensory systems to the fitness payoffs, that's all it can do. And since the fitness payoffs don't have information about the structure of the world, almost surely, then evolution cannot tune our sensory systems to the structure of the world. It can't do it. It's just impossible. So that's one style of proof. And then the other style of proof was that even if you ignored that problem, that the fitness payoffs don't have information about the structure of the world, it turns out that it's just less efficient to compute the structure of the world when all you need is the fitness payoffs. And so we have a second kind of proof. So there's just no way, in other words, that evolution would tune us to the truth. The information isn't there. And even if it was there, it would be foolish to tune us to the truth anyway. It's irrelevant. Great. So that's a real kicker. So now people have to sort of pay attention, right? It's not just some cognitive scientist saying, I think maybe evolution didn't shape us to see the truth. Now there's theorems on the table. And now there's a couple kinds of responses that you can have to those theorems. I mean, every theorem makes assumptions. So someone can try to go in and say, well, I disagree with this assumption in your theorem, right? And try. So for example, we assume that all the fitness payoffs functions, all the potential fitness payoff functions that could be used in evolution, we give them all equal weight. We have a uniform measure on them.
So, Professor, before we get into that, I think there's lots to unpack here. So,
Sure.
love to sort of unpack it bit by bit. So, just to backtrack a little bit, what I hear you saying is David Marr, your guide, his view was that the objective reality exists. So, for example, if I see an apple on the table, the apple really exists. And because the photons from apple fall on my retina, which is 2D, it is my brain's job to construct what an apple in 3D could look like. So that is what you meant by when you said inverse inverse perception, right?
Inverse optics, yes.
Inverse optics, sorry. So, right. But that led you to asking, what if the apple doesn't exist at all? What if the entire thing is just an interface? And I think what I find beautiful about your idea is that you directly introduce evolution into why that might occur. I mean, there is no reason per se for interfaces to appear out of nowhere. But when you talk about evolution and the need for an organism to outcompete, suddenly why that might occur might make sense. So, so when you said fitness payoff, what exactly did you mean? What did you mean when you said evolution wants us to maximize fitness payoffs, and then why would it evolve interface for maximizing it?
Right. So you're absolutely right about your interpretation of David Marr and what he was saying, that we recover the true structures that we need of the world. And that's the typical view among my colleagues in this field. So you're right about that. And the fitness payoffs. Now, in evolution, in some sense, fitness is a very technical term. Strictly speaking, your fitness is simply your reproductive success. Having kids, passing your genes to the next generation. Very much like in a video game, how good a player you are depends on, do you survive this level and get to the next level of the game, right? If you get to level 20, then you're a better player than someone who got to level 2. And so so there's that technical notion. Now, when we turn, a guy named John Maynard Smith in the 1970s, a British mathematician, used the tools of game theory to turn Darwin's idea about natural selection into a mathematically precise theory. That was a big, big move. And in that precise mathematical framework, you have this notion of fitness payoffs, that if you have a certain strategy, so now you abstract a little bit. Instead of talking about just animals and plants and so forth, you talk about strategies. And strategies interacting with different strategies will have different fitness payoffs. And those payoffs do translate into the chance of that strategy reproducing and dominating other strategies. But you can talk about now, if this player with this strategy interacts with that player, how many points do they get? And how many points does the other player get? And in some sense, after you've played a number of games, you add up all the points, and whoever has the most points gets to reproduce more into the next level. So it's those fitness payoffs, which are like the points in the game, that I realized or are essential, right? That's what's governing everything. They're like the utility functions in neural networks. You have a utility function that you're using to train a neural network. Well,
so fitness payoff in some senses, how much do I feel it is useful for me? If, for example, its usefulness to an agent, right? If in the most abstract sense.
Right. And I'll be very concrete. There's a game, a hawk versus dove game, right? So you have hawks versus doves. Now, when the hawk strategy is to always fight and always escalate. So when a hawk meets another hawk, they're going to fight, and that's going to cause some pain. It's going to cause some damage. You're going to have a negative payoff. But if you win, you'll get some points for winning, right? So when you're a hawk versus a hawk, you get damage to yourself, so it's negative points, but you also, if you win, you get positive points. So one hawk will end up really damaged and no points, the other one will get. But a doves always, they meet and they never fight. They agree to flip a coin, and whoever wins the toss wins the points. Okay. So when two doves meet, they will get no injury, and they will get some payoff. One of them will get some payoff for winning. Now, when a hawk meets a dove, the dove always backs down. The hawk always wins, right? So now you can start to play. You can say, so suppose I give you lots of points for winning and only a few points for being hurt. Then it's going to be favorable to be a hawk. But suppose it costs a lot to be hurt, and but you get a lot of points for winning. Then you can play the mathematics. You can find a set where now it's better to be a dove. Now, if you're all doves, if everybody's a dove, then a hawk is going to win, right? It's going to be really wonderful to be a hawk. But if you're all hawks, all of a sudden it's not good anymore, right? Because you're getting, every time you interact, there's a real chance of being. So you can start to see the complexity of this in this real simple game. The payoffs for winning versus the penalties for being injured in the process. These are the kinds of fitness payoff, strategies that we start to think about. But you can have many, many strategies interacting, dozens and dozens of strategies. It becomes really complex and even chaotic. You get chaos happening. So it's really quite interesting.
So in your research, what you found out was, imagine if there is a world and there are two agents. One agent is maximizing for truth, and the other agent is maximizing for fitness. You'd find that if these two agents are put in the world, the one that's maximizing fitness would win, almost by definition, right?
That's right. It takes less time and energy, and you're focusing on the only thing that matters. It's like playing a video game. If you focus on anything except getting points, you won't get to the next level. It's just that's the big intuition here.
If you're focusing on getting better at the game, then it makes sense not to worry about the walls and computer chips and so on, and just focus on the game mechanics and be good at game mechanics.
Exactly right. And we can push that analogy even further to say, suppose that you're a computer geek that actually could, use, change the voltages in the computer. So you could actually toggle voltages and so forth. If you tried to win the game, say you're playing Grand Theft Auto and you're trying to win the game by toggling voltages, and someone else just has a steering wheel and a gas pedal, who's going to win the game? It's real clear who's going to win the game. Seeing the truth will not help you. It will make you just too slow to compete.
Right. That's a beautiful answer to one of the things that was in my mind when I was reading your book, that why can't an agent perceive the truth and then decide what to do versus just blindly doing whatever maximizes fitness. But what you're suggesting is the two-step process is just more costly in terms of time, energy, and the other one would just beat if they were like in an evolutionary game.
That's right. I mean, to be a world-class game player, you don't need to know anything about circuits and software. And if you know everything about circuits and software, there's no guarantee that you're going to be a world-class game player. And all that evolution is about is getting world-class game players. That's all it's about.
Right. Yeah. So do you have any examples of, I know your claim is that everything we see around is actually not reality. It's the user interface. But in your book, you do give lots of examples of illusions, which point and illustrate this point very beautifully in terms of visual illusions and so on. Can you talk a little bit about that, how that just illustrates the point you're making in terms of objective reality not existing, physical reality not existing, sorry.
Right. So we see the world in terms of three-dimensional objects in space and time. The image at your eye, the retina of your eye is only two-dimensional. And so anytime you see in 3D, you are hallucinating whatever you see. You're creating what you see, right? Because it's not there. And by the way, this is the same thing is true for robotic vision systems, the passive vision systems, that they'll have a two-dimensional sensor, a camera or a video system. And from that two-dimensional image coming into the video or to the camera, you've got to use quite a bit of software to recover the 3D or create a 3D interpretation if you're going to like drive a car. So now that doesn't prove that what we see isn't the truth, right? That's not a proof that what we see is not true. It could, what I just said is completely, and these illusions are completely compatible with the claim that we're just recovering the truth, right? That we lose information in the projection from the real 3D world into our eyes, and so we have to recover that truth. So that's why the illusions themselves aren't enough to convince even my colleagues in this field that we're just creating an interface. That's why I had to go after evolution. But I should say another. It's one thing to use evolutionary theory, and that's powerful, but an obvious question is, well, surely the physicists have an opinion here that's pretty important. It's one thing for cognitive scientists to say that 3D objects aren't reality. 3D objects moving around space and time are not reality. But physicists surely would beg to differ. They would say, that's what we study. We're the experts in this area. Move over biology, move over cognitive science. We're the experts here. But it turns out that the physicists themselves are realizing that space-time now itself, which has been, at least since Newton, assumed to be fundamental. Of course, in Newton, it was space and time separately. Now it's space-time together. But yeah, since Einstein. But still, the notion was that space and time, or space-time, is the fundamental nature of reality. And physics has been about what happens in space and time. And now physicists are saying things like space-time is doomed. There's good reason to believe that it's over, that space-time has had a good run. It's been a very useful tool, a great framework for hundreds of years, but it cannot be fundamental, that there's something deeper, that space and time themselves are not the fundamental nature of reality, which is what I'm saying from an evolutionary point of view. Space and time, and therefore the contents of space and time, like physical objects, are not fundamental. And that's huge, right? Because that's been the reductionist paradigm, the successful reductionist paradigm in science for centuries. We assume that space and time is fundamental, physical objects are fundamental, and by going to smaller and smaller and smaller scales in space and time, we get to more and more fundamental laws. That's why we have these huge accelerators like the Large Hadron Collider. The idea is a reductionist, and it's been very powerful, reductionist idea that as we go smaller and smaller, we get closer and closer to the real fundamental laws of reality. Well, but now physicists are saying that space-time itself is not the fundamental nature of reality. And there's several reasons. But first I should point out, you can see right there that already that's agreeing with what I'm saying, right? If space-time and its contents aren't the fundamental reality, there's something else. And by the way, the physicists don't know what it is, right? They don't know what this deeper reality is. It's just not what we thought it was. Space and time is what we thought it was. It's not.
Yeah, in physics, every time a new theory comes along, it just talks about how what we thought was fundamental is not fundamental anymore.
And that's the power of science, by the way, right? Some people might say, "Oh, that shows the failure of science." No, for me, that's the joy and the power of science is that we have these very rigorous models, and they might stand for centuries. Space-time has been great for centuries, but eventually our mathematics and our understanding gets to the point where we realize, the theory itself tells us. I mean, by the way, it's our theories of space-time themselves, Einstein's theories, for example, that tell us that space-time can't be fundamental. So the theories themselves are so powerful that they tell us where they stop. They tell us that there's got to be something deeper. And I'll just say briefly how the theories tell us that. When you take Einstein's special relativity and you bring it together with quantum theory and gravity, what happens is to look at things at smaller and smaller scales in space. Intuitively, you need to look at something with light, right? And light has a wavelength. And so if you want to look at something that's really, really small, you have to have light with a very, very small wavelength. If you have a huge wavelength, you're trying to see something that's really small, you won't be able to see it. So you need a really, really small wavelength to see really, really small stuff. Well, quantum theory tells us that as the wavelengths get smaller and smaller, the energy is going up and up. Energy equals Planck's constant times the frequency. So as we get smaller and smaller, we're putting more and more energy. That's why the Large Hadron Collider is like the biggest machine we've ever built. This is making huge amounts of energy focused in tiny, tiny spots, because essentially you need that energy to see small. Well, here's the problem with gravity and Einstein's theory. Energy and mass are the same thing. They're convertible. And as you get more and more energy into a small region to look, you're getting more and more mass. But then because of gravity, at some point, you create a black hole. And so as you try to look at something really, really small, you destroy it. You destroy the very thing, the very possibility of getting any information from the, and if you get frustrated and say, well, I'll try harder, you put more energy, the black hole just gets bigger and bigger. So space-time itself, the right way to think about it is the very concept of space-time ceases to make sense. It has no operational meaning beyond a certain scale. And we know what that scale is. It's 10 to the minus 33 centimeters. So you're not going to be there anywhere. I mean, it's really, really tiny. 10 to the minus 43 seconds, 10 to the minus 33 centimeters. It's not that there are pixels of space and time, like there's tiny 10 to the minus 33 centimeter pixels. That's not the right, it's just that at that scale, space-time ceases to be coherent as a concept. It falls apart. But it's not even just at the small scale. At any fixed size rooms, take a big size room, and you're trying to measure something like the mass of an electron or something like that. Quantum theory says that you have to have an apparatus, a measuring apparatus, which is a quantum system, plus the thing that you're measuring, like the electron. And to get more and more precision about what you're measuring, like the mass of the electron or its coupling and so forth, you need to get more and more degrees of freedom in the measuring apparatus, because it's also a quantum system with its own uncertainty, right? And at some point, again, you'll get so many degrees of freedom in the measuring apparatus that the whole room collapses into a black hole. So once again, so it's not even just about the very, very small. This is now a large room. This is macroscopic. And so once again, quantum mechanics and gravity together are saying that space-time is not fundamental. The way the physicists put this is there are no local observables in space-time. No local observables in space-time. Now, in other words, there's nothing inside space-time that you can measure precisely with quantum mechanics. And you might say, well, who cares, right? I mean, we can measure stuff to 10 decimal places, 12 decimal places, so who cares that we can't measure it with absolute precision? But what physics has taught us is that we have to pay really close attention to what we can measure precisely, right? So like in quantum theory, there's the Heisenberg uncertainty principle, which says you can't measure position and momentum simultaneously with ultimate precision, right? The uncertainty between them has to be greater than, the product of their uncertainties has to be greater than Planck's constant. And you might say, well, but we can measure it to 13 decimal places, so who cares? Well, it turned out that the quantum physicists, by paying really close attention to the Heisenberg uncertainty principle, discovered that we had to let go of the whole framework of Newton. It's not just that we have some imprecision. It's that we need to completely change our framework of how we think about things. And so by paying close attention to what we can precisely observe is really important, because it changes the entire conceptual framework. And now what physics is telling us is that space-time itself is the thing that's only imprecise. It's only imprecise.
So when you're describing this, it just occurred to me that then it perhaps the right way to talk about these well-proven theories like theory of relativity and others is that these are useful models of reality, and also useful models of reality at a certain scale. And beyond those scale, these models break down. And then what we are really doing when we are studying these theories is we're studying the theories of the interface and not necessarily the theory of an underlying reality, because it wouldn't break down if it was a theory of underlying reality. So
I agree.
this sort of I guess we didn't talk about your interface theory that explicitly. So Professor Hoffman, love to learn more about the basics. What is the interface theory of perception? And yeah, I mean, please describe that.
Right, and I think that you said it very well, that in some sense what this suggests is that physics hasn't been studying objective reality. It's been studying something else, right? And I'm proposing that what that something else is just from an evolutionary point of view, just the set of sensory programs that evolution gave us, right? The interface. So the idea would be that just like when you play a video game, the video game lets you control the diodes and resistors and voltages and magnetic fields in a computer, even though you may be utterly ignorant about those things, may not even believe in them. You may have no background at all. It doesn't matter. You can control them. You're controlling that reality, even though you're utterly ignorant about it. And so that's what evolution has done for us. And it's given us a sensory system that presents shapes and objects and colors in a three-dimensional world with a dimension of time, right? So it gives us a space-time framework, puts objects in there, sounds and smells and so forth, all within this framework of space and time. But based on the theorems that I mentioned, evolutionary theorems, since none of that is the structure of objective reality, I mean, it's provable that the probability is zero that any of that's the structure of objective reality, and yet it's somehow useful. That's why I decided a really good metaphor for this is a user interface, right? Or you could think about it as a virtual reality game, right? A headset, a virtual reality headset that allows you to, for example, if you're trying to do data visualization, suppose you have, you're trying to understand Twitterverse, right? There's millions of Twitter users, lots of stuff trending. Less now that the United States president has been kicked off Twitter, but you know, you have this vast social network of data, and you're trying to, you can't read all the tweets. There's tens of millions of them, and you can't interact with all the Twitter users. But if you want to see what's trending in India versus the United States, what's happening in Bangalore versus New York, you need some kind of visualization tool. And we could imagine, a virtual reality headset with some nice visualization tool that uses colored objects, eye candy that we can understand to see what's going on in the US versus India versus Russia, China, and so forth, that gives us a picture. And that's another good way of thinking about what evolution has done. It's given us a virtual reality headset for visualizing whatever the reality is, because we can't deal with that reality. And it's just too complicated, and we don't need it to survive. Now, that means that the very notion of scale that you mentioned earlier when you were talking about that is just the wrong notion. It's scale is a property of space and time, from large scale to small scale. That very notion may just be the wrong notion, at least a spatial notion of scale could be completely wrong for whatever objective reality is. So now, why has reductionism worked so well for physicists? Well, and in science more generally, it's been spectacular since Newton. Reductionist and the scientific method has been incredibly powerful. And I think it's because we've been studying our headset. And within the headset, it is true that as you go smaller and smaller and smaller, you're getting to more fundamental aspects of the headset. And so that's been very, very useful. But at some point, we've gotten so far along that we realize, whoa, this is just a headset. And so now there are physicists like Nima Arkhani-Hamed at the Institute for Advanced Study at Princeton and others who say space-time is doomed. It's over. There's something deeper. And we have to be adventurous. We have to, guess mathematically what the deeper structures of reality might be. And then you're constrained because they have to project back to what we know. It has to look like quantum theory, relativity theory, back in space and time. So it's not like these are just random guesses. They're highly constrained. It's highly mathematical. It's serious science. But they have to guess these deeper structures and then show that they project back and give us back what we have, the hard-earned understanding of space and time that we do have. We have to get that. And eventually, if I'm right, we'll have to, whatever this deeper reality is, we'll have to show whatever its dynamics is, it has to look like evolution by natural selection when we pull it back into space and time. So reductionism has worked, not because reductionism is right, but because the way our headset works, it's been useful to look at our headset at finer and finer detail until we get to the point where there's no more finer detail. In fact, the headset itself ceases to make any sense, I'd be honest. And then our mathematics, our science tells us time to take a leap outside of the headset. Science so far, 99% of all science has been only a study of our headset. We've never actually studied reality beyond our headset. But science is up to the task. I have no doubt that the tools of science, we've really sharpened the tools studying our headset, and now we can use those tools to, for the first time as a species, take a step out of our headset and begin to explore what's outside of the space-time headset.
So that's amazing perspective, which is generally not very intuitive because we are so embedded in the physical world. I mean, if I go and tell my mom that this table, this chair doesn't exist, she wouldn't believe me. But what you're suggesting makes sense, because just to paraphrase what you're saying, imagine there's a reality which is arbitrarily complex. Your theorem, which is fitness beats truth, suggests that close to probability zero, an agent will perceive that reality as it is, and with close to probability 1, it rather actually exploit that arbitrariness for whatever payoffs it can have. And by payoffs, it means whatever aspect of the reality helps it propagate from like a reproduction point of view. And even reproduction might be very sort of organic nomenclature. I realize what you're talking about is maybe one level deeper and more abstract, but whatever helps that agent sort of outcompete other agents is what that agent's reality will become, right? But the underlying reality will remain hidden from that agent.
That's right. And you've summarized it very well. And I should point out a couple of things. One is that there's been some recent work in deep neural networks from DeepMind. There's a paper. The paper is titled "An Investigation of Model-Free Planning." Then it's free. You can go online and just Google "An Investigation of Model-Free Planning," the DeepMind paper. The first author is a guy named Arthur Guez. And they've discovered the same thing I'm talking about, that in the past, they've been trying to train these deep neural networks on the real models of the world that they're trying to get them to work in. And they've discovered that it's better to just have the utility functions allow the deep neural network to train itself. You don't give it any model, you don't tell it the truth, and it builds its own internal model, which isn't the truth, but is adaptive. And it allows the deep neural network to solve the problem. It effectively builds its own interface. And so what I'm saying from an evolutionary point of view has been discovered independently by the researchers at DeepMind in their deep neural networks. But to give an intuition about this that I think would really help people. Again, think about someone playing Grand Theft Auto, right? When we say we're not seeing reality, now if you're playing Grand Theft Auto, you're seeing a steering wheel. And you could say, well, it's true that I'm seeing a steering wheel. And there's a sense in which it's true, you're seeing a steering wheel and you're seeing a gas pedal and you're seeing the other cars. But if you say, well, but is that is that what the real reality is that you're interacting with? You'd go, well, no, okay, I know there's a supercomputer. So there's a notion of truth to the steering wheel, right? Yeah, it's true that I have to grab the steering wheel. There are rules of the interface. If I try to steer by pressing on the gas pedal, I'm not going to be steering. I'm going to be in trouble. And if I try to use the steering wheel to push on the gas, then that won't work. So there are rules for how to use the interface. And in some sense, there's a reality of the interface, but it's not the deeper reality. There's a much, much deeper reality that's being hit. And so that's when I say that, the moon is only there when you look, right? It's not the fun, and space and time are only there when you look. It's just like the steering wheel. If you have a VR headset, right, and you're playing Grand Theft Auto with a VR headset, if I turn my headset over here, I don't see the steering wheel because I'm not rendering a steering wheel. It's only when I look over here and I render a steering wheel that there is a steering wheel, because there is no steering wheel in the computer. And it's in that sense I'm saying, when I look at the moon, I render a moon. But when I look away, whatever reality is continues to be whatever it is, and it's not a moon. But when I look at, so there is a reality. There is an objective reality, and it's utterly unlike anything that we see. But and that's for good evolutionary reasons, right? It would be too hard. I mean, it would just be overwhelming. Just like the Twitterverse thing, it would be overwhelming data to see all the tens of millions of tweets and so forth, or billions of tweets. You just couldn't do it. So our interface has to dumb things down. That's its purpose. And that idea then leads to some other really profound changes in how we think about things, right? Right now, our intuition is, if I see something and it looks stupid, that's because it is stupid, right? A rock looks stupid. But now think about it this way. I have an interface. Reality is whatever it is. Reality could be exquisitely complicated and even intelligent, perhaps. But my interface is going to have to give up at some point. That's the whole point of an interface. So things that are going to look really stupid to me, even though I might be interacting with something whose intelligence is far greater than mine. I mean, for all I know. So the distinction, so this is a real profound, this will give people a real sense of how dramatic this change in concept is. The distinction that we make between living and non-living things. Right, we'll say, well, human brain is living, of course, a cat is living, an ant is living, bacteria is living. By the time you get down to virus, I don't know. But by the time you get down to protons and neutrons, absolutely not. They're not living anymore, right? So we have this idea. And if I see a rock, of course, a rock isn't living. Well, my attitude is now not so quick. We have to be careful. Our interface is taking really brilliant stuff and dumbing it down. It's making it look stupid for us just so that we can survive. So when I see something that looks really dumb and not alive, the question is it because I'm interacting with something that's dumb and not alive, or is it because my interface is just hiding the truth? And so the distinction between living and non-living now gets called into question. We have to be far more subtle and deep in thinking about that distinction. My guess is that our distinction between living and non-living is entirely an artifact of our interface. Entirely. That's my personal belief.
It's sort of like looking at a computer that's not doing anything and believing that nothing's happening. But in the background, the computer could be syncing files, could be uploading data, could be actually running lots of programs just to keep that computer look idle. But all that complexity is hidden by that plain desktop that we see in front of us.
That's right. It could be doing trillions of operations per second and you wouldn't know it.
Right. So, Professor Hoffman, I wanted to ask, let's say I'm an agent in Grand Theft Auto, the game, and that's the world I know. Why should I care about what's beyond, what's the objective reality, if that is the only world I know? If physical world is the only world I know, why should I care what's beyond? And second, you said that science is up to the task to peer into that. I don't know, it's still an unsolved problem, but what structure of such a program do you see? How do we even begin to peer into that unknown?
Right. Well, so what was the first part of your question again?
Why? I mean, if all my life I'm embedded in this physical world, why should I care about
Right. And then how do
a
we
deeper
actually see the world?
underlying reality?
Right. Well, I think for a lot of people, they probably don't care, and that's perfectly fine. There's lots of things that I don't care about that other people do care about, and that's perfectly fine. I think for scientists, and for certain other kind of philosophers and certain kinds, and then just certain people would have a certain kind of inquisitiveness, right? That for example, what happens when you die? I mean, a lot of us are interested in that. I mean, and the kinds of answers you have about is space-time the fundamental reality have implications for what happens when you die, right? But if you are simply your atoms, if your consciousness is nothing but the activity of your atoms, and the atoms in your brain are the fundamental reality, then it's very, very clear that you cease to exist. There's nothing left of you. So for a lot of us, we have some skin in the game, right? That makes this of interest to us. I mean, it's of more than passing interest, whether or not death is the entire end or not. That's a genuine question. So there are intellectual reasons, but I could understand why someone might say, don't bother me. This is good enough. I'm enjoying life, and this is perfectly fine. For scientists and philosophers and certain other people, it's an important question. We're just trying to understand what kind of creatures are we? How are we situated in reality? What is reality? Is it possible that our deeply held beliefs about reality are deeply wrong? Could we really be wrong that badly? And if so, is there any chance for us to get a deeper insight into reality? I should just say one reason why we believe the physical reality is the truth. And this is from an evolutionary point of view again. The child psychologist, Jean Piaget, proposed that children before 18 months of age don't have what he called object permanence. They see a doll, and as long as they see it, it exists. But if they look away, it ceased to exist. They don't understand that objects remain. But around 18 months of age, he said, they get object permanence, and you can sort of test it. If you take a doll, the child plays with it, and take the doll and put it behind a pillow. Before they're 18 months of age, they won't go looking for the doll behind the pillow. After 18 months of age, they'll go looking for the doll behind the pillow. And so you go, okay, they finally got the concept that objects continue to exist even when they're not perceived. And later research showed that we actually get object permanence much earlier, maybe 3 or 4 months of age. So from an evolutionary point of view, we've been programmed to believe our interface is the truth. We believe in object permanence by 4 months of age. Before we can even reason about it, we've been pre-programmed that I see the moon, that's because there is a moon. I see a cat, that's because there is a cat. And so we're programmed with object permanence. So as adults, we have always believed our entire life that what we see is the truth. We've been programmed. So that's why it's so hard for us to accept this. It's not because there's any logical reasons, right? If you look at any logical reasons you might give, well, I know that the book is there even when I don't look, because if I look away, you can see if the book is there, right? So that shows, but I can do that in virtual reality. If I'm playing virtual reality Grand Theft Auto, and there's a red Mustang over there, I can look away and say, well, my friend can look and see if the red Mustang is still there, and say, oh yeah, I still see it. But no one believes there's a real red Mustang, even though your friend says he's seeing it. That's just because he's rendering it when I'm not rendering it. And if you go through every argument that people give about why the object has to exist, just play that same argument over in virtual reality, and you realize the argument doesn't go through. It's just silly.
Right.
So now your question was, how do we get science to go beyond, right?
Yes.
What do we do?
And you have a theory about that network of conscious agents. So would love to understand more about it and how the testable predictions it makes, which is necessary
Yes.
for a scientific theory.
Right. And I should say that these are two separate ideas now. So the first idea is that evolution by natural selection entails that we're not seeing the truth. That's just a theorem of evolutionary theory. Okay, so I'm just saying, let's take evolution by natural selection. What does that theory tells us? It tells us we're not seeing the truth. That theory does not tell us what's beyond, what's behind space and time, right? So now I'm making a separate hypothesis. And so you could buy the stuff about evolution and not buy what I'm about to say. They're completely separate things. So that's the first important thing. If what I'm about to say seems like nonsense to you, that's perfectly fine. It's independent of the work on evolutionary theory. And you could propose your own theory of objective reality, or you could try to go back to evolutionary theory and try to change evolutionary theory, right? You could try to change evolutionary theory so that our theorems don't hold anymore. Those are all options that you can take. But so now I'm trying to ask what's beyond space and time. And of course, the right answer is I don't know. Right up front, I don't know. We have to guess, right?
Okay.
But as scientists, what we do is we make our guesses with mathematical precision. And then we try to make predictions that we can test. That's what we're up to. And by the way, the physicists themselves are in the same boat. They're saying space-time isn't the fundamental reality. What's beyond? We don't know. We're going to guess. But our guesses will be constrained. We will make mathematically precise guesses, and then we will see if we can get predictions that we can test. And the guesses that they're making are things like something called an amplituhedron, cosmological polytopes. These are mathematical structures that they're finding. Right now, what the physicists have they're finding these beautiful structures that can give rise to space-time, but they have no idea why those structures are there, right? It's just like, okay, here are these structures, but who ordered that? Why? What's going on, right? There's no notion of something going on beyond space-time. There are just these static structures right now beyond space-time that they're finding. And the question is, okay, so why are we finding these structures? What's up? What's up? So I'm in the same boat. I don't know what's beyond space-time. I'm having to guess. But I'm guessing a process. So I'm proposing, and here's my reasoning. I may be wrong about everything I believe. But if I'm right about anything, I'm right that I have conscious experiences. I have a headache, or I smell garlic, or I see the color red, and so forth. If I'm wrong about that, it's not clear that I really should try to do anything. I mean, it's not clear. I mean, how can I make any progress? So I'm going to take it as a given for building a theory. We'll see how it works. That there are conscious experiences and entities, maybe not humans, not necessarily humans, but a wide variety of entities. I'll call them conscious agents. Then we have to then define precisely what we mean by it. But human beings could be conscious agents, but we're not the only, and maybe not even the most typical kind of it could be a wide variety of conscious agents that have conscious experiences, maybe an infinite variety of conscious experiences or a large variety that I can't even imagine, right? So I'm not trying to be human-centered here in any way. It's just conscious experiences and agents that have them. And the idea would then be, we've been trying to understand consciousness because we all like to understand our consciousness. Well, a lot of us do. And right now in neuroscience, we've been trying to figure out how consciousness comes from brain activity, right? That's been the model right now, is that brain activity somehow causes conscious experiences. Well, space-time isn't fundamental. Its objects aren't fundamental. That means neurons aren't fundamental. They don't have any causal powers. Objects in space and time have no causal powers. That's stunning, right? That's what we're saying. No physical object in space and time has real causal powers. There's a useful fiction of causality, like in Grand Theft Auto. If I'm turning the steering wheel to the left, I have a useful fiction that the turning of the steering wheel caused the car to turn. And that's perfectly fine in the game to have that belief. It's a useful fiction, but it's just a fiction. The steering wheel actually has no causal powers. In fact, it doesn't even exist when you don't look at it. So everything, when I hit a cue ball and it hits an 8-ball, it's a useful fiction to think that the cue ball caused the 8-ball to go into the corner pocket, but it's just a fiction. And so neural activity is a useful fiction for explaining human behavior, but it's just a fiction. In everyday neuroscience, I use it. I talk about area V4 causing color experiences or whatever. It's very useful fiction, just like it's useful fiction to say, turn the steering wheel to the left. The steering wheel to the left will cause the car to go to the left. It's very useful, but it's just a fiction. Well, so if brain activity is just a useful fiction, it doesn't cause consciousness, how do we explain the relationship between consciousness and brain activity? That was my problem. The relationship between consciousness and brain activity. If I take a magnet and touch it to your skull right here, to area V4, and inhibit it, you will lose all color experience in the left part of your visual world. You'll still see color in the right part of the visual world, but you only see a black and white, like television picture, black and white TV on the left side. Take the magnet away and color comes back. There's a clear correlation between brain activity and conscious experiences. And there's dozens and dozens of these neural correlates of consciousness. The question is, as a scientist, is how do we explain them? And evolution tells us you can't start with neurons and boot up consciousness because neurons are just useful fictions. They don't do anything. They're a useful fiction. So my motivation was to say, let's start with consciousness. Not a hand wave, a mathematical model of consciousness. So that's what we're doing in science, a mathematical model of consciousness. And then I have to show how that model of consciousness gives rise to spacetime, which is what I'm working on now. And then once we figure that out, why in that space-time interface, we get things that look like brains and neurons. How do those arise as symbols for this deeper dynamics of consciousness? And then we can start to solve this problem of consciousness and its relationship to the brain. So that was my motivation. So the idea then is reality is a huge social network, like the Twitterverse. There are conscious agents, and just like in the Twitterverse, you have people that tweet and follow. In the conscious agent social network, there are agents that are communicating with each other. They're listening to some and not listening to others, and they're broadcasting their ideas to some and not to others. So it's very much like the Twitterverse. So it's all mathematical in the sense that when we study the internet, it's network information theory. It's a mathematical realm called network information theory that allows us to start to analyze the dynamics. Why does Google get all the hits on his website and Hoffman gets no hits on his website? There's things like that you can begin to understand, right? So, and there's the rich get richer kind of thing. The more hits you get, the more you're going to get, and so forth. So there's all sorts of. So there's a very rich mathematics of network information theory that we're using to now try to model consciousness, and I should say. There's an important distinction that needs to be made, and that is between a model and the reality. As a scientist, all I can do is write down mathematics, right?
Yeah.
But the mathematics isn't the thing that you're actually studying, right? If you build a simulation of the weather, you don't need to bring an umbrella into the simulation room. You're not going to get wet. The computer simulation will not create rain. And similarly, my mathematical model of consciousness will not create consciousness and is not consciousness. It's just a scientific model. So consciousness is whatever it is, and conscious dynamics is whatever it is. The mathematics that I'm proposing is simply trying to be precise about our claims about consciousness. And so, and the reason for that is people in various religious traditions, as you well know, have thought about consciousness for thousands of years. And it's, both in East and the West in religious traditions. And people have thought about consciousness for a long time. We've never had any mathematical models of it. And the reason we need mathematical models is, if you think about it, we're not much further advanced than the writings from 3,000 years ago, right? We in fact still cite those same writings and study them. In science, we don't cite things from 2,000 or 3,000 years ago and study it. It's really not necessary anymore, because those were really good ideas back then, but because we have mathematical models and testing and so forth, we can move along. So we need to do the same thing in consciousness. And the real big move here is to say, we can do it with consciousness. Consciousness, no less than anything else, can be studied by mathematics. Again, I'm not reducing consciousness to mathematics. I'm not saying consciousness is mathematics, but I'm saying the attitude is this: if we really want to learn something, we need to be precise. We can't just hand wave. Do we really want to understand consciousness? There's only one way. Well, of course, there's the first-hand experience, being a conscious person and meditating and so forth. That's very important. But that wasn't enough to understand the physical world. We were all in the physical world. It took the genius of Newton and Galileo and Copernicus and all. It took precision, Einstein. It took being mathematical, saying, this is what we're experiencing. Let's write down some mathematics. And then all of a sudden the mathematics comes back and slaps you in the face and tells you things you didn't expect. Like Einstein, when he wrote down his mathematics of general relativity, it took him like 8 years of intense work to write down the mathematics. He had the big idea. If you're falling in an elevator, you'll be weightless. That was the big idea. That, and it took him 8 years to turn the idea that if you're in a falling elevator, free falling elevator, you'll be weightless, to turn that into, his tensor mathematics of. When he did that, a year later, someone came along, a guy named Schwarzschild came along and said, hey, you know what? Your equations say that that space-time will create black holes. And Einstein said, I don't like that. And Einstein was, the equations came back and became the teacher even of Einstein. So if Einstein can be tutored by his mathematics, then how about the rest of us mortals? Einstein's intuitions were so profound and deep, and yet they were not profound and deep enough to realize black holes or to realize that the universe was going to be expanding. He didn't. That was also a consequence of his theory. So it's absolutely important in understanding consciousness for us, of course, to have firsthand experience, to pay attention, maybe to meditate if you meditate. But it's not enough. We'll be stuck in the same conversations 5,000 years from now if that's all we do. The only way our conversation about consciousness is going to really move ahead in the next centuries is if we get serious about making mathematical models and making risky predictions where we can be wrong. And that's the point. It's about making risky predictions where you can be wrong. It's not about dogmatically defending an idea because it's 3,000 years old. That's how you don't make progress. The way you make progress is to be absolutely humble and say, look, the sages have had great ideas. Let's study the ideas. Let's try to make them precise, and then let's try to see where they might be wrong. We have to be willing to find out where we're wrong. If there's anything that's can't be touched, if there's anything that we won't allow ourselves to go there and question, that's probably the thing where we will stop our progress. And so It's this humble attitude. We be precise so that we can find out precisely where we're wrong and we can make progress. And that's the idea.
So when you were talking about your guess that reality could be a network of conscious agents, I was imagining that many people may find it shocking and unbelievable. But then in the history of science, for example, all we knew first was heat. And if you would have told people that heat was nothing but the motion of atoms, they would not have believed, because it was not just evident, it was not obvious. But when heat was reduced to motion of atoms in a very statistical way, you could make all sorts of prediction that could open up into new predictions about heat. And that's what you're talking about, that when you reduce, if your guess is true and reality is indeed composed of network of conscious agents, putting a very precise mathematical theory on top of it could teach you things about reality, because reality is composed of it. And if it turns out to be true, it just lends credence to what you're talking about.
Exactly right. And so that's what we're doing. I have a team that's working with me. It's a lot of mathematics, and we have a mathematical model of consciousness. And I can just tell you the big picture of what we hope to show. That if you look at a network of conscious agents interacting, it's too complicated to see step by step everything that's going on, each tweet that goes. What do? You have to look at the long-term behavior, what we call the asymptotic behavior, the trends, like what's trending. But there's a whole mathematical set of tools for looking at trends. It's called the asymptotic analysis of Markovian dynamics and so forth, or dynamics on graphs. My hope is to show that asymptotic dynamics of conscious agent dynamics gives exactly the structures that the physicists have found behind spacetime. The amplituhedron, the associahedron, the cosmological polytope, that these structures, they're wondering where the heck did they come from? I'm saying those structures are just the asymptotic description of a really complicated process of consciousness. And the reason why physicists have never seen consciousness is because spacetime has always been just an interface that dumbs things down. So, and one way it dumbs things down is to not look at the details. Think about it this way. Suppose that look at freeway traffic. There's thousands of cars on the freeway. Each one has a little conscious person driving the car, hitting the brake, turning the wheel, and so forth. But if you're in a helicopter, 1,000 feet up, looking down, it just looks like little particles moving through arteries, right? The freeway arteries. And you could give fluid dynamics, physics, and forget consciousness. And that's what physics has been doing. They've only been in the helicopter 1,000 feet up. They can't see all the consciousnesses that are running the different cars. They just see the fluid dynamic description. If that's right, then I'll be able to give you the description of all the conscious agents, the details of the Twitterverse, how it's working, show how the trends are what the physicists are seeing in terms of the amplituhedron, and then the physicists show how to go from there into space-time. So half of the work is done for me. I just have to meet them halfway, then they can take me all the way into space-time. So that's sort of my goal. And there's a lot of work ahead to do. If anybody's interested, the mathematics involved is network information theory, a branch of mathematics called geometric algebra. That's the mathematics of space-time. It unifies special relativity and quantum information theory. They turn out to be unified in geometric algebra. And then there's the study of the physics that's needed, amplituhedron. There's some lectures given by Nima Arkhani Hamed at Harvard in 2019 on this. In other words, the work, there's some serious hard-nosed mathematical work to be done. And for anybody who's listening who has mathematical skills, I mean, we're talking PhD level mathematical skills are required for this work. It's non-trivial. But the top level picture is network information theory for the dynamics of consciousness, Markovian dynamics on that, dynamics and graphs, looking at the asymptotics, study the asymptotics, polytopes that come out of that, and then the physics. That's where physics then kicks in and show how space-time arises. My goal, just one quick thing, my goal is to go from dynamics of consciousness to predict scattering amplitudes of 2 gluons in, 3 gluons out at the Large Hadron Collider. When I can do that, when I can go all the way from a dynamics of consciousness to predicting the precise scattering amplitudes for particles at the Large Hadron Collider, we will have finally gotten the connection. That means we have the bridge. Now we can build on it, right? That's not the end, that's the start. That will be just the start, because then we have to build up chemistry, biology, neuroscience, and finally the whole thing. But I think we have to start at the base and get gluons. How do we get gluons scattering amplitudes from this theory of conscious agents? Once we get that connection all the way through, by the way, then we are reverse engineering our interface.
Right.
And the technology, we will play with space and time themselves. We will be able to warp space and time. So the technologies that are going to come out of this are going to be completely mind-blowing. Everything right now is firecrackers compared to what we're going to have.
What I love about this is, it's not hand wavy philosophy like everything is conscious. I mean, Hinduism and a lot of philosophy does talk about it, which is beautiful. But what you're pursuing is a formal, mathematical, rigorous, and testable program where you model conscious entities in your mathematics, and through their modeling behavior, you're trying to sort of connected to what physicists observe at a very fundamental level. And you're suggesting if the behavior of dynamics of conscious agents is able to emerge as some sort of fundamental particle behavior, then you have that bridge
That's right.
to make a lot of additional predictions, which could lead to a lot of new technology, which we can't even imagine right now.
Absolutely. Absolutely. So that there's going to be a real test of whether we've got it or not. And this brings up another interesting thing. Some people will say, well, because I'm saying that we don't see reality as it is, I'm sort of a postmodernist. I have walked away from the Enlightenment ideals of reason and searching for truth, and I've gone into this postmodern fictional kind of thing. It's all just a story, and who cares? And astrology is just as good as science and so forth. And I want to make very, very clear, I'm not a postmodernist. I'm looking for a true theory. And when I say that space-time isn't fundamental reality, I'm saying that in the Enlightenment sense, that it's not true that space-time is fundamental. I'm claiming that that's a false claim. And I'm hoping to find, and maybe I won't, but I'm hoping to find a deeper structure like this conscious agent networks and I'm hoping to find a true theory. And so it's not relativism and postmodernism or anything like that. I believe in reason. I believe in looking for true theories, but I believe in being very, very humble. Our theories so far are not true. And we just have to accept that they've been great guides, and their power is to tell us where they stop. Space-time is not fundamental. They're telling us that. Evolution is telling us that. Special relativity and quantum theory and general relativity together are telling us that. They're telling us that space-time isn't fundamental. And we have to look beyond. Now, we'll never know if our theories are true. Even if my theory makes tons of predictions and every one of them is confirmed, it doesn't mean I'm right. And that's another point of humility here. This is the human epistemological condition. We have to, what we can do is say, if I don't get true predictions, there's good reason to believe I'm probably wrong somewhere, and I need to figure out where I'm wrong. But even if I'm right in every prediction, that just means I've not been clever enough to find the experiment that will show me wrong. And so that's the attitude that we have to. So there's a fundamental humility in the process of science, and that's the real sort. We're rigorous. We're mathematically precise. Individual scientists, of course, are dogmatic. People are people, but as an institution, science pits one dogmatic scientist against another dogmatic scientist, and that's how we avoid dogmatism as a science. So yeah, many theories only die when their authors die in science as well as other. And that's understandable. That's human nature. But as an institution, science is a humble institution because it's killing off its theories. And there are no demigods. You win the Nobel Prize, but if you say something that's stupid, we're going to call it out and say it's stupid, right? So there's no worshiping of someone who just because they have a Nobel Prize. We listen to them because there's a good chance that the next thing they're going to say is smarter than me because they've won the Nobel Prize. But again, if we have good evidence that they're wrong, then they're wrong. So it's this humble thing of being precise with mathematics, knowing that you can never know for sure that you're right. And so therefore always being non-dogmatic as much as you can personally, but science as an institution has to be non-dogmatic. And eventually science will let go of space-time. Even though science has used space-time as a foundation for centuries, it's going to take a while. There's inertia. But I bet, a century from now, with the new progress, space-time will now be viewed as a useful concept that had its day, and there's something deeper, and science will have moved on. And we want to have the same thing in conscience. We want to take the insights of the sages from thousands of years past. There are deep insights there. So I'm not saying ignore the past. Absolutely not. We should study, but non-dogmatically. We should try to learn and then question. Even question the sages. Learn from them, question our own ideas, question everything, and try to move on to the next level of our understanding.
Right. So, Professor, I know we're a little bit over budgeted time. If you have maybe 10 more minutes, I just have a few more questions.
Sure.
That I would love to get into. So the first, the follow-up question that I wanted to ask: how far along in this journey of building a fundamental theory of reality based on consciousness are you or your colleagues? How far have you gotten along?
Well, we have a couple papers that we published. One's called Objects of Consciousness. So if you just Google Objects of Consciousness, you can see the fundamental mathematical model. And then there's another paper where we started to study some of the network properties of it. But there is an enormous amount of work ahead. And the challenge here is the range of mathematical talents that are required. You have to know network information theory. You have to know quantum field theory. You have to know polytopes. You have to know amplitude hedrons. You have to, the list goes on and on. You have to understand the Birkhoff the list just goes on and on. So I am spending all of my time learning mathematics because in some sense you have to to make this big connection all the way, you have to know all the pieces. You have to be able to see all the pieces. So I'm working with real mathematicians, but I spend hours every day just studying the mathematics. And I retired early, so I could do this. I mean, okay. It's just there's no time if you're teaching and committee work and so forth to really. So I've got to focus in. So I retired and I'm just learning as much mathematics and then thinking out of the box as much as possible. So there's a lot of work ahead, and I invite anybody who's got interest in the mathematical, PhD level skills. It really requires PhD level skills to jump in.
Okay. So talking of mathematics, if it may be true that physical reality is not real, and when we do physics, we are doing physics on the interface. We are proving things on the interface. What's your view on mathematics and logic, which is independent of physics? I don't even know whether asking mathematics is real makes sense or not, but love to see how do you sort of characterize mathematics?
Is mathematics invented or discovered? That's one deep question about mathematics. And is mathematics, in some sense, related to consciousness at all or not? How is mathematics related to consciousness? I mean, if I'm using mathematics and consciousness, what relationship do I think that they have, right? And the question about whether mathematics is invented or discovered has been a deep philosophical question for a long, long time. Some really interesting work was done by a brilliant logician named Kurt Gödel around 1930 or so. And Kurt Gödel he proved that that there is, I won't go into the details, it's called the Gödel's incompleteness theorem. So if people want to read the details about it, you can just search Gödel's incompleteness theorem, Godel, but they call it Gödel because it's an O with two dots on top of it. So Gödel's incompleteness theorem, without going into details, it entails that there is no end to mathematical structure. That no matter how much mathematical structure is discovered, you've only just begun. Even God, so to speak, could never know it all. That's the deepness of this theorem, that there's an endless variety of structures. And so that really takes the question about, is mathematics invented or discovered? It makes it really, really interesting, because what on human level, we're discovering new theorems all the time, right? And the question is, are we inventing those theorems, or are we discovering them? Or is it both? See, there's an open-endedness to mathematical structure, and it's quite possible that the very activity of discovering the structure is the same as inventing the structure, which is really quite interesting. And
Yep.
the relationship with consciousness is interesting. One field that I've worked in quite a bit is called psychophysics, where we do experimental studies of human conscious experiences. Color, for example, there's color space. We use for cameras and editing images and so forth. All the work that's been done on human color perceptual space is very, very helpful in practical ways. So it turns out, when we study human conscious experiences, we find they're structured. That is, we can write down mathematical structures. For example, red is more similar to orange than it is to green. And we can write down that similarity relationship in terms of an order relationship, or some kind of non-Euclidean geometry of color space and so forth. So in everywhere we turn, we find mathematical structures. So consciousness and mathematical structure are not alien to each other. Every conscious experience, every specific conscious experience, has a mathematical structure. And so you could think, at least at first blush, that the relationship between consciousness and mathematics is like the living organism to the bones. Without the bones, at least if you're a vertebrate, right, you're going to be in trouble, right? So you need the bones, but there's more than just the bones. And it's sort of, there is structure to consciousness, but there's more, it seems like there's more than just structure, right? And so that's right at the limits of my understanding, right? So that's, but what it does indicate to me is that mathematics is quite relevant to the study of consciousness, right? That's very, very clear from the study of psychophysics. We get mathematical models of conscious experience all over the place. So it's relevant. The deeper question, I don't have an answer. But here's the thing I'm playing with. Something I call Gödel's candy store. Right? That Gödel tells us that there's an endless variety of of mathematical structures. And no matter how many you discover, there are more to discover or invent. The fact, if we assume that consciousness is fundamental, as I'm doing, I could be wrong, but let's just play the game. Consciousness is fundamental, it's all there is. Every conscious experience has structure. Under that framework, that means the fact that Gödel tells us there's an infinite variety of structures to explore means there's an infinite variety of conscious experiences to explore. So maybe, a question that someone would ask me is, if consciousness is fundamental, what is consciousness doing and why? What is it up to? What is this all about? Well, Gödel's candy store is the only idea that I've found that is deep enough and to be a possible answer. I'm not saying it's right, but it's at least deep enough to be a contender. What consciousness is up to is exploring Gödel's candy store. There's an infinite variety of conscious experiences to be explored, and so let's get on with it. Let's go. Now, that's Gödel's candy store. It sounds like it's all fun and games, right? Now we know that some of our experiences are not fun and games. So, right. So there's going to be an aspect to this that's not just fun and candy, but it's rather that to explore new conscious experiences is also to let go of what we already know and to go into the unknown. And even kids in a candy store, they, I like chocolate. Well, why don't you try this one? No, I want the chocolate. I want to stick with this chocolate one. We have this reticence to move on and explore. And so there may be a lot of what goes, the negative side of life may be just our resistance to letting go of what we already know and exploring what's ahead. And if this model is right, it's in the essential nature of consciousness to explore, enjoy, let go, and to go on and to keep exploring. And so it may be that a lot of the negative emotions we have in life are the clinging to what we already know, to the candies we've already had, and the conscious experiences we already had. And maybe what's really required, and it's a continual learning process, is to let go of the experiences we've already had and open ourselves to brand new experiences. And this may be, again, where the mathematics and the science really dovetail with spiritual traditions of meditation, right? In meditation, in which you go into absolute silence, you really are letting go of all structures that you know. If you really do it, and for, to do that, it can be scary. It's like you feel like you're at sea. I'm letting go of everything I know. Everything I know are the comfort blankets that I've had, they're my safety blankets, and so that may be part of this whole dynamic. Again, I'm not saying this is right, but at least it's Gödel's theorem is deep enough that it could be that there's this deep mathematical principle, in principle, an endless exploration of mathematical structure, which in this context means an endless exploration of conscious experiences, which means an endless letting go of what we already have experienced and an endless opening to new experiences, which is, once you fully give into it, can be joyous, but the letting go part can be not so joyous. Yeah, it's very much like, I was surprised to read about the process of metamorphosis. A caterpillar creates a cocoon, goes in, and comes out a butterfly. And we go, oh, how beautiful. I mean, I came in a caterpillar, I went out a butterfly, it's all joy and love. Well, it turns out, no. Inside the cocoon, the chrysalis, there's a war. The immune cells of the caterpillar take the cells that are trying to convert it into a butterfly as enemies. And so the immune system tries to kill them, and it kills them and kills them and kills them until it gets overwhelmed. The caterpillar fights and fights and fights against the transformation. Eventually it gets overwhelmed and it turns into a butterfly. But think about it. Everything that the caterpillar knew, I eat leaves. Well, it's no longer going to be able to eat leaves. I have a bunch of legs that I crawl. Well, you no longer have a bunch of, you got 6 legs now instead of how many you had before. Now you got wings you've never had before. Everything that the caterpillar knew and loved has to die. And its immune system fights it tooth and nail until it gets overwhelmed. So that may be why, even though I talk about Gödel's candy store and it sounds great, ultimately it is great. And for the caterpillar turning into a butterfly, ultimately it is great. But there's going to be that battle that goes on before you finally turn into the butterfly and reap the benefits of being a butterfly. And so that may be, so that's a long answer to the mathematics thing, but you can see why it's complicated.
Yep.
And I don't know if I'm right, but at least these are fun ideas to explore. And I would love for someone to propose another idea, a completely different idea about what consciousness is about, that's deep enough to be a serious contender for why consciousness does something and what consciousness is up to.
Right. So what you're suggesting is, because our conscious experiences have some sort of a structure. So for example, in color map, it's just not arbitrary. Orange is definitely closer to red. And this in some sense suggests that conscious experiences, they are an expression of a mathematical structure. And what might be happening under the hood is, if we have by default some structures, and by virtue of it some conscious experiences, they could be infinite number of structures, which could imply infinite types of conscious experiences, which can possibly get instantiated in reality.
Right. The only place I would say things maybe a little differently is to say, I don't know if it's infinite. It's unbounded.
Okay.
But there's and it may be infinite. I'm not saying it's wrong that it's infinite, but I just want to put out the possibility that Gödel's thing may be that the structures are unbounded and you can never come to the end, but it may not be infinite. I don't know if it's infinite.
Okay. Okay. So, Professor, just the last question to end this wonderful conversation with, how does your research inform your personal life or beliefs? I mean, you definitely have internalized that physical reality per se doesn't exist. Does it impact the way you live, the way you behave in the world, or your beliefs in any way?
I've discovered that the change in how I see the world is remarkably slow. It's happening, but it's not like, oh, okay, now I just see the world differently. I have object permanence just like the 4-month-old, right? and so my knee-jerk reaction is, of course, the moon is there when I'm not looking. And of course, I mean, so that's just the sort of default. But nevertheless, when I'm reflective, it's very easy for me now when I'm thinking about things to see this as all an interface and be quite excited about it. And also, I do meditate, and so this has informed my meditation, and the meditation has informed my scientific work. And there I do then use these ideas to look back at what's going on in the meditation, to think about the transformations that are taking place and the emotions that come up in terms of this deeper picture. And I again, I'm probably wrong, but at least it's a framework to try to understand what's going on. And if you have a framework, then you can try to revise it and get a better framework. And so it's useful to me in that way. I find it useful to have something to reflect on after I come out of the meditation. Of course, you're not reflecting on it in the meditation if you're doing it, if you're in silence. But yeah, I would say for other people. And by the way, I haven't done psychedelics, so there are people who have done psychedelics, and sometimes there's like a transformation. You're in a different state, and I've chosen not to do it. And maybe if I had done it, maybe that together with the intellectual work I would be there. I don't know. So I don't think that my path is what everybody's path is going to be. So I think other people may get there, like in the experiential sense, far more quickly than me, and maybe others will be more slow than me.
Okay, great. Thank you so much. This has been a really wonderful conversation. I've learned a lot and enjoyed every bit of it. Thanks for taking time out today, Professor Donald Hoffman.
Thank you, Paras. It's great pleasure.
Bye-bye and take care.
Okay, take care.
Thank you.